Hello and welcome to this short presentation on Robot Guidance Simplified with Machine Vision. I'm Neil Sandhu. I'm the Product Manager at SICK for Machine Vision, LiDAR and some of our other systems, as well as being the current UK IVA Chairman. Just a little bit about SICK. As you may or may not be aware, we're a global company based out of Southwest Germany, but now having offices pretty much in most locations around the world, over 10,000 employees, and over 40,000 different automation product solutions. But we do spend a lot of our revenue into R&D, as you can see. So we're always trying to create, innovate, and come up with some fascinating and interesting and helpful new solutions, including what we're going to be talking about today with regards to robot guidance. So a very short agenda, just to talk to you about machine vision technology in general. Then we'll look at some different robot types, how different technologies with regards to machine vision and robotics can be helpful, and then finally regarding the technology where SICK can actually come in and help you. So if we look at the differing machine vision technologies that are typically out there in the market, we think about vision sensors where we have inbuilt optics, lensing, lighting, all the processing is done on board. Even the communications is self-contained, and the configuration of such devices is very straightforward. Do it in minutes via either software or using a web browser. So a very, if you like, entry-level based self-contained vision solution. Moving onwards, we go to smart cameras, which are, if you think upper level regarding the functionality, extra tools, better resolutions, but still keeping that inbuilt style with all the lensing, optics, lighting, which is obviously crucial when we talk about machine vision, and so all the processing on board, still, all self-contained. Then we move a step further to programmable cameras, where a little bit more expertise is needed in terms of the language used to program such a device, perhaps from lower level programming languages, and the development of these can be sometimes taken on by rather than end users, systems integrators, or specific vision companies. And again, you can have inbuilt optics and lighting, all the processing can be done on board. It's just the programming of these devices can be a little bit more advanced, but that does give you the possibilities of having bespoke and tailored levels of inspection to suit the application and challenge specifically, and that really can come into its own. And we can also, on the same train of thought, talk about streaming cameras, and these are cameras that are basically designed to acquire the image or data in a very fast way. If the name suggests, they stream the images that are taken of whatever's being inspected to potentially something like an industrial PC or sensor integration machine, for example, that can receive all this information, and that hosts software solution or software to do the actual image processing and create the decisions of inspection. If it's good, if it's bad, where is it located, for example, in robot guidance and things like that. So we have various different realms of machine vision that are possible. Now, a little bit about the differences between 2D and 3D machine vision. As you can see here from the example, we've got the same object, in this case a food box containing some food products, and we have some images obtained using a 2D system and a 3D system. And just to refresh everybody's memory, the differences of where 2D machine vision, 3D machine vision can be used are broken down into quite straightforward descriptions in terms of looking at 2D being contrast based. So you look on the two left-hand images, contrast being a typical image, for an example, that is the sort of image that you take with your smartphone. So you can see the detail, you see the if you like, the top left image, the logo, perhaps to check it's the right product, is the logo in the right position, and on the bottom left image, do we have product in all 4 segments of the packaging, which is very nice and straightforward to do with a contrast-based system. But if we look at the 2 right-hand images based on 3D, 3D is really about acquiring the height information, the height data. So when we take a 3-dimensionally based image from the same 2 standpoints, you see that the surface detail is more displayed on the top right image in terms of the top of the packaging. So potentially if it's been damaged in some way, if it's creases, if it's sticking up, is there a piece missing perhaps or folded up, then it would be detected in this way. And in the same respect, from the actual product inspection bottom right, not only can we tell if there's product present, but we can also see the height of the stack in this case, and we can detect if something is amiss here. And that's what the height information can give you when it comes to this 2D or 3D style of inspection. So if we think about different machine vision technologies and how they can come in and help with robot guidance, we think about, let's say, for example, 3D machine vision, and a typical technology that's used within 3D machine vision is something called time of flight. Here we see an example of time of flight 3D vision, and you can see there the energy that's being emitted from the device, typically infrared energy, invisible energy, light, should we say, and all of those areas, if you like, individual pixels, are then monitored to see how long that energy takes to come back, and we get the 3-dimensional distance information that builds up, as you can see here, the 3D picture in the example on the palette. And also, if we look on the right hand side now, the scene here that you can see in an office where it's taken the data to look at the chair that's present, the end of the corner of the wall with the cupboard and the boxes, and the different depth perceptions behind that. And that's all possible using time of flight. So where can this type of technology be useful? As you can see here, if we can take an image in this style with a snapshot 3D capture, you can see we can start to get dimensions of different objects. Here in this case it's boxes, but also that can then help with, in this example, the palletization or potentially depalletization of product from pallets, and robot picking in general. If you can get a good idea of the size of the object, where the object is located, so then the information can be passed to the robot and the next steps can be taken. And here an example of 2D machine vision where you have a typical camera, as you can see there on the left, inbuilt illumination, as we spoke about before with smart devices, that is triggered and then illuminates the scene with its inbuilt lighting, takes the picture, and then you see on the right hand side, for example, if we have a product or an object that needs to be localized for robot guidance, because it's contrast based, we can detect it in front of its background, calculate its coordinates, be it the camera coordinates that can be transformed into what we call global world coordinates, so the robot understands where within its environment it is located, its orientation, so we talk about X coordinate, Y coordinate, and angular orientation. And again, this information can be passed to the robot for automatic picking and for next steps in any process. And here we see an example of that with the same device as we showed just before, taking a picture, and it's triggered. The object is seen, as you can see here, located, detected, information sent to the robot for it to carry out its picking, in this case to place on the next part of the process. So let's now look at some different types of robots that we work with regards to machine vision, and take you through that. So just some relatively basic examples of the different types that we've worked with throughout the development of some of this technology. If we think about something like a SCARA robot, where they're typically used in smaller applications, they're usually at a fixed height, and they're very good at very simple travel in either an X or Y direction to be picking or placing, that sort of thing. The articulated arm on the top right has many joints There could be many of these junctional joints, so it could be rotated in and positioned in lots of different ways to get a lot more movement, let's say, than a SCAR robot, and not only in X, Y, but also in Z. The Delta robot, bottom left, typically is a very fast-acting picking robot that's used in a variety of industries where speed of pick is of the essence. And the bottom right linear Cartesian system, again, typically similar to a SCAR but on a larger scale in terms of being very good in XY movements, and its Z-axis height is fixed to a degree in terms of a set range. Some examples of the types of applications we see by looking at these robots and what's needed in terms of where we need machine vision to help robots with their guidance and what they're seeing. Here you can see in front of you now regarding picking items, either small or large, from a belt or from feeding systems, packaging, packaged products coming down ready to be packed onto pallets or for the next stage of the shipping process, even to the degree of tending a machine. If a robot is designed to even control the starting and the stopping of machines and picking out the items that have been created and produced, is also possible with using a robot. And even taking a stage further from that machine, picking, if you like, kitted parts, so making sure they pick in the right order to place either in packaging or to construct a full component by placing part 1 onto part 2 onto part 3, etc. So that's all possible, and this is all the examples of robot applications that we've worked with. Many more, but some of the ones that come to mind and really stand out. So if we think about machine vision working with robots and providing guidance for the robot, we really are providing the eyes to locate and guide that robot, would be at whatever type, to accurately pick or localize and action whatever the next part of the process can be it from a static position, a moving position. And even so, if you look on the right hand side, some of the vision sensors nowadays can be mounted directly on the robot arm. So in terms of a positioning or a frame that you see on the left, potentially you could mount the sensor on the robot itself, and it could actually position the sensor where it needs to be placed to make sure it takes the picture for the inspection or localization that's needed in the best position. And the more examples that we see, including the kitting of the parts that we see on the left here, can be done not only in 2 dimensions but also in 3 dimensions, making sure that the different heights of the different parts that information is passed to the robot, so as when to come down and pick, it's done in the right way and not damaging any kind of or causing any damage to any of the products. Excuse me. The middle example there is quite a common one we're seeing now regarding produced parts that are obviously placed in or delivered nowadays in bins or stillages, and these randomly orientated parts need to be picked in the right position, in the right way, at the right point to be placed on the next part of the manufacturing process. So identifying where they are, how they are orientated, and also picking them in the right position to make sure that they're placed correctly for the next part of processing or packaging is extremely critical. And that, with machine vision technology that's been developed over the past few years, is now possible, as well as on the right hand side where we see larger parts that potentially could be placed in racks for, again, picking for the next part of the manufacturing process. That next part needs a very precise alignment, be it in this case on these automotive parts, gluing or on positions specific within that part, or placing for welding, and they obviously needs to be very accurately placed. So the alignment of the vision system to tell the robot exactly where that part is, as it could be lying slightly angled on a rack, is very, very critical. And again, that now is possible with developments in machine vision. So machine vision for robots based on image capturing, be it 2D or be it 3D, are really helping and enlarging that field that the robots can be used, and providing much better guidance to make sure that the robot utilization is at the optimum. And it really helps now that we've developed lots of new things within the machine vision world that can really assist and make robot usage a lot more easier, simpler, and quicker to get to grips with and to get deployed. So if we take it a stage further, you can actually see there that regarding machine vision, in this case 2D vision, not only can we find parts, but we can sort them. We can find multiple parts of the same type to make sure that in this case on the left with the feeding system of these parts, that information is passed to the robot to say where these parts are, where they are, how they are orientated, to make sure that they can be picked very quickly and efficiently, to make sure all of the parts are acted on very quickly to improve production cycle times. And looking at the right example, small parts as well as very large parts, as you see here, can be handled, and regardless of orientation or position, they can be located, detected, and accurate information passed to the robot for picking. And here we see again the examples briefly mentioned before, where sorting, identification of different parts is possible, not just where are they, but which one is it, and therefore the right program of picking can be decided upon to pick in the right order, especially for kits of parts. And that can be applied, as we see as well on the right, to things being placed in a static, stable position, or even something that's moving on a conveyor belt. And with 3D vision technology, we really can help in the realms of perhaps challenging products, as you see here, these natural food products in the images shown, where the packaging is varying to a degree, the heights aren't fixed. So being able to ascertain the height information really does then help the robot in this case to pick and come down and place itself at the right position without causing damage to potentially a product, in this case a natural food product, that could be very easy to damage if too much pressure was applied by coming down to a fixed height below the actual height of the product. So we see here as well with 3D using, in this case, a laser triangulation, you can see that even using different technologies, you can look at different materials, even a perhaps semi-transparent bag in this case, and still detect the information needed to provide accurate guidance to the robot to pick. And if you look at the example on the right, not only can we do this guidance for localization and locating the parts or products or objects, but we can also multitask. As it's a vision inspection system as well as a guidance system, it can actually start to inspect for quality. So as you see there with the example of the food product on the right, if it's too thin or too out of spec or not produced in the right way in terms of its missing a component in the manufacturing world, then this can be inspected for and then acted upon with regards to even passing the information to the robot, to another separate data collection system, to make sure that the incorrectly made parts or objects are not picked. And also with three-dimensional technology, you can see here on, in this case on the left, it's what we call an AMR, autonomous mobile robot. In this case, it's what we call a little, almost like a cart that will detect where it needs to go in terms of underneath this movable shelving or dolly. And with 3D technology, as you can see, we can start to inspect for the right place to guide the mobile robot to go drive underneath, in this case, and lift up the dolly or movable shelving to drive to the correct location. And on the right hand side here, in terms of spot welding, in this case automotive, but it could be a lot of different industries, we can detect a part that's come in on a moving conveyor accurately to within the very high precision to make sure that the welding robots know exactly where the part is. So, how can we help you as SICK? Well, we've been working in this technology for some time now, and we've developed partnerships with various robot manufacturers where we can take our vision systems and have pre-written interfaces, communications drivers, if you will, already done, where you can then start to actually work with the vision system from the robot pendant itself. And that is something that really makes using these systems and combining vision and robots and deploying a system to get to work actually happen in minutes rather than hours or days. So the hard work is done. We can do that as well because we've now decided to take on designing and creating software for the vision systems based on the app technology. So we all have the smartphone. We choose the apps that we want on our phone to give us the functionality of the phone. Well, we do the same thing now with machine vision, where we can create robot guidance systems, inspection systems that are simple apps to download onto the same hardware, so you can almost treat a camera a bit like a smartphone and choose different apps to do different tasks. And that means very simple to install, very easy to potentially change over if ever needed to be, and you get up and running a lot faster. In this case, let's say robot guidance applications are already pre-written, and that leads to very simple to use software to create the configurations needed to carry out the tasks efficiently. So from robot guidance on picking from belts, picking from feeders, to inspecting labels, inspecting electronic components, picking large parts, guiding moving autonomous mobile vehicles and robots, and doing various different types of inspection. These app-based solutions are all available for use, and they've been, as said, pre-written, so making installation and deployment a lot more straightforward. Here at SICK, we've also created pre-written solutions for those examples spoken about earlier, where picking randomly orientated parts out of a bin or larger parts from racks can be possible with simple plug-and-play based systems now that are very straightforward to set up. So let's now show you some examples of what we can provide from SICK. First one here is typically the same concept that we showed earlier in terms of the technology behind 3D snapshot machine vision to dimension parts or boxes, and then provide positional information for, in this case, palletizing, but it could be any kind of picking and placing operation, palletizing, depalletizing, picking parts to place in next parts of manufacturing processes or assemblies, etc., etc. And that all comes from our 3D time of flight and stereo vision cameras that we can provide. Also, using the similar technology, we can apply the 3D machine vision concepts to mobile robots or autonomous mobile robots or mobile vehicles for anti-collision and navigational purposes, where you can see the three-dimensional zone aspect can be created to make sure not only at the single layer level but also in a three-dimensional space that the operation is performed correctly in detection of empty spaces, but also other vehicles and potentially other obstacles can be done to make sure that the operation of these mobile robots is done to the optimal level. Using 3D technology, in this case, we're going to be showing you some laser triangulation and talking about our app-based solutions that we've done on the smartphone analogy. Here you see one of our 3D devices showing a laser line, showing laser triangulation technology as the food products come down, semi-transparent bag or actual smaller objects, that you can see that the technology can provide the information at a very fast speed, varying heights, varying different materials, to make sure that they can be picked up from a moving belt in this case. And again, using the same concepts here, not only are we talking about individually picking up items, but we're talking about the orientation of them as well. So here you see these simulated food products randomly orientated, and then can be positioned accordingly back in the correct packaging to the right accurate degree. And using 2D technology that we spoke about before, we can have our part localization systems, again based on the app concepts that's created just to download into a smart device, a feeding system here that's feeding different objects or placed already in an array, can be picked at a very accurate level, regardless of orientation, and positioned for the next part of the process or for packaging very accurately. And that all comes from having, in this case, a static 2D camera taking a picture of the scene, identifying the parts, in this case in the right order. We talked about kitted parts earlier, to be picked and placed, and that all comes from this one smart device where everything's self-contained. Optics, illumination, communications. Here we see the 3D snapshot technology again that we showed you earlier, this time on another autonomous mobile robot. There it's positioned at one of the ends of the vehicle, and then can inspect the position of the movable shelving or dolly to make sure it guides the mobile robot into the right position before that mobile robot can then lift up its upper platform to move the movable shelving to the right position. And again, that all comes from 3D snapshot technology. And you can see that the level of the information and the data that we get from this 3D depth perception to a very high degree. It's simple to program via a web browser, simple to set up, and so easier deployment and quicker get to runtime. Using exactly the same device but with a different app, we can look at something very similar in terms of locating for either manned or autonomous mobile robots or forklifts, where the application uses the 3D depth perception to find the correct positions for the forks to go on a pallet, be it in a bay or racking, be it on the floor, and that is very straightforward to set up again from a web browser. All the tools have been pre-written and the communications, so the information when the detection is occurring is automatically passed to the vehicle or mobile robot for the forks to engage and the next part of the operation to continue. Here we see more 3D vision from SICK, providing, in this case, to a customer over in Europe regarding picking out of a bin where the random parts are produced to make sure they can be then correctly aligned for the next part of the process. Here they're making automotive components, and as you can see there, they're cast, they're placed in large containers. We have a robot guidance system there sitting above the actual container or stillage or bin, and it identifies the parts no matter what position they're in to make sure they can be accurately placed, as you see here, for the shipping and for the next parts of the process. So they're going into the assembly of the vehicles, and those parts are in the large container you see below the robot, and they are trained via 3D models or CAD to make sure that the vision system can accurately locate in any orientation within that bin. And that's the nature of what we call our part localization for bins, bin picking. So those are just a few examples. Something else that we're working on at SICK now is our digital area, in terms of not only are we providing the inspection and the machine vision to work with these robots, we can also provide data analytics. So if you want to know how well the system is performing, if we look at remote access and preventative maintenance, by making sure we can check on the quality of any parts, as well as how well the robot is performing, then we can provide the digital offering to make sure all of those analytics can be monitored remotely or on premise with various cloud-based solutions as well. So that's all possible now with SICK, with our new digital systems. So by looking at simple gateways that link to sensors on the shop floor, sensors mounted on robots, we can get the data from those sensors, be it metrics on how many parts it's picked, or how many pallets it's filled, or how well the sensor is performing itself. Is the sensor getting dirty? Is it getting to a stage where it needs to be cleaned before potential operation could be affected? All that information can be contained and ascertained from our sensors into a gateway system, and then that gateway system can then distribute that information and visualize it either even on a mobile device such as a phone, a tablet, a smartwatch, to the level of a PC, somebody in a higher level system in terms of the enterprise level, looking at quality systems and data. And it can also be distributed to any cloud-based platform that we can work with as well, which is most of them. So simple dashboard can be created to view those metrics, set alerts and alarms to make sure if something is occurring that perhaps could be showing signs of operationals being affected, then it can be dealt with before it actually causes a major issue. So that is all from me. Hopefully you've seen there that the technology is really coming on in regards to machine vision and robots, and it's making it a lot easier to get to grips with, to deploy, to use robots themselves to make sure that operations can be increased in terms of efficiency and performance. And here at SICK, we've also been working in that area to hopefully make you all aware that machine vision and robot guidance is much more accessible perhaps than it used to be. Thanks very much.